Okay, let's do the second part of section 2.2. Can probably pick up right where we were. So let's go to there. Okay, one-to-one correspondence. That just means we can line up the elements in one set directly across from elements in another set. For example, we can say that the set, let's call it A, and the set B here are one-to-one. And they're not equal. A does not equal B, but A is equivalent to B. They have the same number of terms, so they could be lined up one-to-one. Now, if we want to know all the ways we could line them up, we're certainly not going to make a table. And I'm not going to go through this. I'm going to go directly to the fundamental counting principle. This is huge. It comes up in all sorts of math, statistics, probability. Now, an event, M. So remember, A, I think, was 1, 2, and 3. And B was A, B, and C. Well, there are 3 elements in A. So A can occur in 3 ways. Same thing with B. B can occur 3 ways. So what we do, the total number of ways these could be aligned is 3 times M. 3 times 3 is 9 ways. M times N. Let me do just very quickly one more example of this. Let's do ATM PIN numbers. There's 4 slots for your PIN. There's 10 ways for the first digit, 10 ways for the second, third, and fourth, because you could have 0 through 9 as a digit in your PIN. The counting principle says multiply those together. That's 10,000. So there's 10,000 different ATM PIN numbers that we could generate with 4 digits in a PIN. Okay, talked about equivalent already. So we could say A is equivalent to B, but it doesn't mean that A is always equal to B. Equal sets are equivalent, but equivalent sets are not necessarily equal, because equal means you have the same elements. Okay. Let's look and see if any of these are equal. So I'm looking for the same elements. Looks like B is equal to D. That's the only one. Now let's look for equivalent. Well, C has 3 elements, so B is equivalent to C, and D is equivalent to C as well. Also, B is equivalent to D. And now we can look at A. A is not equivalent to any of them, because it has one more element. Cardinality, the number of elements in a set. Cardinality of K is 5. How many elements are in L? Well, there is 1. So the cardinality of L is 1. Let's see, X. X is a real number, and X equals X plus 1. That doesn't work for anything. So there are no elements in X. So the cardinality of X is 0. And the same thing here. Y is the null set. There's nothing in the null set. It can be written as like this, a set with nothing in it. So the cardinality of Y is also 0. Talked about finite sets and infinite sets. So the set of whole numbers, notice W adds the 0 to it, to the natural numbers. So these are infinite sets. Now, these are certainly not equal sets. They do not contain the same elements, the natural numbers and the set of integers. I'm going to let you think about if they are equivalent. So you could stop and pause for a second while I set this up. No cheating. Got to set that up differently. Give me one more here. Okay, look what I did by rearranging these. I rearranged the integers. Remember, they're infinite. So now I can line up an integer with a natural number. Since both sets are infinite, I'll never run out of the natural numbers. Therefore, I can do a one-to-one correspondence. And I can say that the natural numbers are equivalent to the integers. And to make sure we use J. Okay, very quickly, looking for equal sets. Looks like A is equal to C. B is not equal to any of them. This is interesting. E is equal to H because they're both the null set. But F is not equal to G because the null set isn't the number 0, but F is equivalent to G because they both contain one element. F is the set that contains the null set. So the cardinality of F is 1. It does contain something. Okay, last part of this section, universal sets. Just everything under consideration. So we're going to do an example where U is the set of X such that X is a member of the US Senate. So if I want the cardinality of U, I believe there are 100 senators. So now we're going to introduce Venn diagrams. So here's my universal set. I tend to put the U up here. It's senators. And I know the cardinality of U is 100. Now, let's look at something that lives inside the universal set. Females, US senators. Notice we have the circle for the female US senators. So my question to you is, what lives out here, this cross-hatched green? Those would be the male US senators. And so we're going to give that a fancy name. The stuff in the universal set out here in the green that are not females, these are the males. We call that the complement of F, written this way. So I'll draw this Venn diagram. Complement of a set A. So if this is a universal set, and here's my set A, the complement is everything that's not in A, but is still in the universal set. So that is a complement. Okay, so here's my universal set, A, B, C, D. Okay, B is C and D, so the complement of B is the stuff that's in U, the elements in U that are not in B, so that's AB. Now, the complement of U. I'm trying to think the elements in U that are not in U, there are none of those. That's the empty set. And so the complement of the empty set, or the null set, complement of the null set is the universal set. Last topic, subsets. So B is a subset of A. So if and only if every element of B is an element of A. And if that's not true, we say A is not a subset of B. And here's where we get equality. If A is a subset of B and B is a subset of A, they're equal. We'll touch on that soon. Proper subsets. Notice here we have our universal set. We have the set A. So B is living inside of A on the Venn diagram here. But notice there's an element in A that's not in B. So B is a proper subset. And we dropped a little dash. And so B is a proper subset of A. Finite sets, if they're equal, we know that they're equivalent, so the cardinalities are the same. And if A is a proper subset of B, then the cardinality of A is less than the cardinality of B. And that's a definition of inequality, less than. So if A is the set A and B, B is the set of A, B, and C, we can see that A is a proper subset of B. And the cardinality of A is 2. Cardinality of B is 3. And so the cardinality of A is less than the cardinality of B. Okay. Oh, counting the number of subsets. So P has one element. So really the only two subsets are the set itself and the null set. The null set is always a subset of a set. So here's R, it has 3 elements. This is not 2 times n, it's 2 raised to the n. So in this case, it's 2 to the 3rd. So the number of subsets is 8. If I said A was the set of the alphabet, then the number of subsets of A is 2 to the 26, since there's 26 letters in the alphabet. That's a huge number. 6, 7, 1, 0, 8, 8, 6, 4. So there's over 67 million subsets of A. Okay, what's something I can touch upon? Let's do this, just to finish. Let's let A equals A, B, C, and D. Let's set B equals B, C, A, and D. Let's set C equal B and C. Well, we can see that A equals B. And if I was to do a Venn diagram for this, this would be A in blue. Then I would take B in red. Well, it's the same thing. It looks like that. So they're equal. So B is a subset of A, but it's not a proper subset because A does not contain an element not in B. But if I write the subset here of C, so now A is out here, I can see that C lives inside of it because there's two elements, A and D, that live in A that are not in C. So C is a proper subset of A. We clean up that C so it doesn't look like the subset symbol. And that is the end of this section.